Welcome everyone to the next live session of Amazon's Consumer Science Summit. I'm Sam Eldersveld, the Director of Research for IPC at Scott, and I'm going to be your moderator for the next hour or so. I'm really happy to announce that our speaker for the next session will be Nassim Taleb, who should require no introduction. Professor Taleb is currently the Distinguished Professor of Risk Engineering at NYU's Tandon School of Engineering. But prior to this, he spent 21 years as a financial risk taker, or what I like to call a quantitative trader, before becoming a researcher in philosophical, mathematical, and practical problems with probability. Professor Taleb is the author of the 5-volume essay on uncertainty that has been published in over 40 languages. This essay, Concerto, includes the volumes The Black Swan, Fooled by Randomness, Anti-Fragile, Skin in the Game, and the most recent volume of this series he will explore today, The Statistical Consequences of Fat Tails. Professor Taleb is also the author of more than 50 scholarly papers in mathematical statistics, genetics, quantitative finance, physics, philosophy, ethics, economics, and international affairs. After Professor Taleb's talk today, we will have a brief Q&A session. So please make sure to type your questions into the broadcast chat bar to the right of the screen in the live session. I note that there have been some people who have noted that their screens had frozen momentarily in one of the previous presentations. If this happens to you, please refresh your browser. And without further ado, I give you Professor Taleb for the next live session of Amazon's Consumer Science.
Great, thank you. Thanks, Sam, for inviting me, and thank you, Amazon. I'm going to say the reason why I'm usually not known for being extremely generous with praise, but Amazon is the reason I exist, because when I wrote Fooled by Randomness, the first volume of the Incerto, nobody carried it. Bookstores said, is it finance? Is it philosophy? They couldn't understand that something could be multidisciplinary. And bookstores did not like to carry my book. But Amazon saved me because, we start to have an online activity. And of course, it led to a market for something that you cannot put in a special section in a bookstore. It's the same thing with because my activities, you don't have, if nobody's paying me to define myself, nobody's paying my salary, I don't have to define myself. It's the same thing with writing. Anyway, so this time I'm writing about, actually it's the first volume of the technical Incerto. It's outside the Incerto. There's a companion, and this is the first of 3 volumes. This one is on consequences of fat tails, which sort of maps to the idea of the Black Swan. And the other 2 volumes, the second one is on convexity, and the third volume is on errors in higher dimensional data, analysis. And the course of dimensionality. This is volume 3 is mostly on when I started getting involved in random matrix theory. I rediscovered stuff I knew intuitively as a trader, and I put in Fooled by Randomness. So my idea of the Incerto is everything that's technical can be technical, but you put it on the side. So this is an idea. The problem, the story of my life with fat tails is as follows. People say, well, now we're going to use fat tail in place of thin tails. Yeah, like changing the color of the dress. This is what I call this error. No, it's different. Number one, we don't understand fat tails. Okay, saying the distribution of fat tails forces you to change a lot of things. And the title of actually this book is Real-World Pre-Asymptotics, Epistemology and Application. Pre-asymptotics, why? Because everything is based that we know on the law of large numbers. That's the philosophical problem of induction. So how many observations you need to be comfortable with your statistical claim, which is a subsection of the problem of induction, and basically we're lost on the fat tails because we can't do the same thing. So before we go further, the way I classify fat tails is at the bottom of distribution is a degenerate distribution, which is basically degenerate is actually a mathematical word. As I know you have so many PhDs, they would know. It's not polite, but it means distribution with no randomness. And then you have the Bernoulli distribution, and then you have thin tails from the standard, sum of Bernoullis becoming binomial, and then you have so really it's never really doesn't deliver infinities. It's compact support, but it's sort of Gaussian by convergence. And then you have a Gaussian that has no compact support, but pseudo compact support. And then you have the cusp is the exponential, sub-exponential, the exponential basically deciding. In that zone, we start entering fatter tail domains. And then as you go to the right here, you have forget about it, means that the law of large numbers will never work. Here, L1 means that you have the norm L1, only the mean exists, and you can't use any higher moments, which is basically standard statistics. And let me explain this with more intuitive presentation now with this following quiz, and then we go back to doing math. I select randomly from the population 2 people, and the total height is 4 meters 10 centimeters. What's the most likely distribution? Okay, well, I mean, not 10 centimeters at 4 meters, okay? So there is a domain, and that's pretty much defines the domain that is not sub-exponential, in which you're vastly more likely to get 2 times 3 sigma events than 1 times 6 sigma event. See? And that domain is what I called in the graph the Cramer condition. And it's very simple. It tells you that if you're going to take a loss as an insurance company, it's going to come from a lot of small hits. Okay? A big loss would be a lot of small hits, not a big hit. Because vastly more likely to get a lot of 3 sigma events than 1 times 9 sigma event or 12 sigma event or so on. So here we have the ratio of the square for 2 independent observation. So it's a survival function, probability exceeding k square over probability of having 2k events, an event of 2k size, in other words, a 6 sigma versus here the probability of having 2 3 sigmas independent. And then you see as k gets bigger how the thing explodes for a certain class of distribution. Now, if I do if I ask you, now you have a random selection of 2 people, and the compound wealth is say $40 million. What's the most likely distribution? I think in the example I used $36 million. $36 million. What do you think, Sam, is going to be the most likely allocation? 18 and 18. At random select, and I have 2 people, and it happens that the sum is 36 million, which is a tail event. See, there is a domain in which you're vastly more likely to get a 10 sigma event than 2 times 5 sigma events, and vastly more likely to get a 20 sigma event than 2 times 10 sigma event. So this, we can explain it very simply here with this graph. The isodensities for 2 independent Gaussians, that on this graph I show that the total, where the total of, this is the isodensities, these are the deviation for one for the other one, and then pretty much that when you have a tail event, but the most likely place is where they're both 4.1 and 4.1. On the other hand, for the other domain, I'm cheating by modifying a little bit because you can't have a negative height, but doesn't matter. Negative wealth in this case. It's either one has 36 million or the other has 36 million, because the joint to independent, okay, will be something called non-elliptical. That's in higher dimension, which is my new interest since I finished this book, this volume 1, which actually is a collection of papers. Anyway, so this is a way to see the difference between these two, or to really see it here in the real world, that if the boss tells you at year end, if you lose more than $100 million, explain to me what events caused them, odds are it's going to be one in fat tails. And this helps us, for example, understand the difference between a lot of things. Why is it that we have to worry about COVID? Although COVID hasn't killed as many people as other diseases, someone tells you, you have a billion people dying in 2022. What it got to come from a fat-tailed thing. Okay, so conditional on 2 billion people dying, odds are it came. You look from a tail to the body, odds are it came from a something that's very fat-tailed, which can be only a contagious, pandemic or a war. The two fattest tailed risk we are facing today. So now, if I die and you want to remember my work or something like that, okay, this slide will explain it all. It's a working of the law of large numbers. So look up top how the law of large number converges very fast for Gaussian. Okay, and look at the bottom for Pareto 80-20 with the same mean deviation, say, how many more observations do you need to stabilize the mean? You see? Pareto 80-20 is in a class of fat-tailed distribution that we saw in the graph up all the way up north, and of course it doesn't have a variance, doesn't have a lot of things. Still, the law of large number works, but very slowly. So you have what I call pre-asymptotics. So here you notice how long it takes, and the best way to figure it out is by looking at the convergence properties, and you notice the following, and this is maybe technical. It's derived in a few papers and it's this book. But if I ask a statistician, I tell him, listen, you need n of 30 for a Gaussian to be comfortable with a mean. How much more n for the drop, to be to lower the variance of your estimator? How much more data do you need for a Pareto 80-20? Typically, they tell me maybe twice as much, 3 times. Let's not exaggerate, all right? 3 times. That was all my life. You know how much more data do we need? You need 10 to the 14 times more data. So this book has chapter 3, which is the less non-casual chapter of the book. And in chapter 3, I cover, the things that the consequences, that's called consequences, the fat tail, the title, the consequences. And consequence 1, the law of large number, when it works too slowly in the real world. Okay, in other words, almost always need more data. So, and it cancels a lot of statistical estimators. So this is the consequence number 1. This is more technical here. I'm defining what do I mean by a certain class called power law, which is all the way at the top. So you have Gaussian basin, and then you have something called the exponential, which is really rare. And then up the top, you have the power law class. And I show visibly why finance isn't a power law class. We showed how pandemics are in the power law class. There are a lot of things in that class. If you're in that class, you need to work on your estimators because you cannot get the mean very easily. So that's the consequence number 1. We can easily verify in the S&P 500. There's a technique called maximum to sum ratio. I won't bore you, but visibly the moments don't converge. You see, people are fooled by the fact that in sample you always have a mean. You put the Excel spreadsheet, you say, average, you get the average, you get variance, you always get a variance, even if the process doesn't have a variance. You see, so but there are techniques to figure out if the mean converges in your sample or stuff to be able to rule out Gaussianity, and effectively we can for the S&P 500. We can for a lot of things. Now the other one, you may tell me, well, you know what? How can you prove to me that it's a power law? But effectively, very simply, very, very, very simply. Okay, if you witness a 10 sigma event, what is called a 10 sigma event in the Gaussian world. Something we observe in finance practically daily, more than once. Okay, you're going to have one variable every day, something in finance that has 10 sigma. And you have days when you have 20, 30, 40 of them. Depends on how many securities you're tracking, you see. So I've seen all my life these 10 sigma, so I knew from the beginning. But that's a very simple reasoning. The reasoning is going to be as follows, okay? If someone tells you it's a 10 sigma event, i.e. the probability is very, very tiny. The 10 sigma happens every 10 to the minus 23. Yeah, sorry, 10 to the 23, days. So you know definitely that it's more likely that they're using the wrong probability distribution than that probability distribution delivered an event of 10 to the 23. And the way I prove it is using Bayes' rule. That unless you have 100% certainty that your distribution can only be Gaussian, okay, unless you have total certainty, you have the slightly non-certainty in your prior. In other words, can be 99.99% Gaussian, okay, and you have a 10 sigma event, then you reject that the probability of the distribution that you watched is Gaussian. And an event here I call survivorship. In other words, probability of exceeding something. So in other words, to summarize, if someone tells you it's a 10 sigma event, it's vastly more likely that that person doesn't know, okay, statistics or distribution than it's a 10 sigma event. See, but that's so common. Like, for example, we had people who had that pseudo Nobel in economics, the Swedish Riksbank's prize, who after LTCM said, "Oh, we had a lot of 10 sigma events." If you're saying that, you cannot say we had a 10 sigma event. Okay, it's not like unless God told you the world can only be Gaussian. You see, it tells you the world is not Gaussian. If the world is not Gaussian, then there are a lot of consequences. And now, a lot of people in finance, a lot of people in economics have said, "Oh no, we're under fat tails," but then they didn't take it to the consequences. The consequences effectively, once you have to rule out something, and then you have to be a little more vigilant on your approach. Now, I use this confirmatory empiricism to prove it, and the logic is as follows. Let's say that I have degenerate distribution, okay, and then once in a while, boom, I have an additional variation. I can rule out it is degenerate. I can say it's random, non-degenerate. But if I see just what I have on the left when I'm pointing the cursor, is the cursor showing? Yes, cursor showing. So when I'm showing the cursor here, can I say, is there evidence that there's no randomness? No. That's the fundamental asymmetry. I can reject degenerate, okay? You see, I cannot accept that distribution is degenerate. So you start ranking, I can reject that the distribution is thin tails. I cannot reject the distribution is fat tail for very same asymmetry, fundamental asymmetry. And that's pretty much the theme of the Black Swan. And that's a Black Swan, the logical Black Swan problem ported into statistics. You see, I can reject, okay, the non-existence of Black Swans, okay, but I cannot reject the existence of Black Swans, okay, unless I've seen all Black Swans, which is, all swans, which of course is inimical to sampling theory. So, consequence number 2, and then we can go with consequences till, we stop here. The mean of distribution will rarely correspond to a sample mean. It will always have a small sample effect, downward and upward, particularly when distribution is skewed. So, and let me explain. If the distribution is skewed, okay, you're going to have where the missing observation to the right in that section we don't see here. You see, above the maximum observation. So there are, there is a mass to that density. You don't see it when you do non-parametric approaches or you do other distribution. So that part of distribution would play a large role for the mean. You see, and that's one. So, and then we made a statement with my co-author Cirillo in our paper on COVID, or a paper on pandemics in general, how they are fat-tailed, and all these things that were, sort of like not understood in discourse. That our central point, we told them, the fatter the tail distribution, the more the tail wag the dog. That means the more you have observations, the fewer the observations that determine all the statistical properties, and all of these are in the tails, okay? So in other words, the body has less and less significance when the distribution is fatter and fatter tail. And for those who are familiar with power laws, it's the alpha exponent of the power law. The lower the alpha exponent of the power law, the more the property comes from the tails, both tails. Now, if you only have one tail because the distribution is just skewed or one-tailed, then you have the richest, the most important part of the distribution is what you do not see. You see, simply, you do not see the most important part. Okay, now we have to figure it out by parametric analysis, and we approach that to something we call the shadow mean. You see, the unseen rare event, try to fill in this based on properties that we derive from the body distribution. So we looked at wars, we looked at we started using the method of shadow mean as filling in the mean from that unseen observation via extrapolation. And who does it? Did it implicitly, not explicitly. The Dutch, when they wanted to build, walls, because they sort of like don't want to drown, which is very legitimate concern on the part of the Dutch. And then they said, we're not going to make the mistake of which actually was made in Fukushima by taking all the past observation and saying, oh, what's the maximum variation? Okay, let's hedge for that. Okay, not thinking that can be exceeded. Okay, so the Dutch started techniques called extreme value theory that effectively allow us to fill in that missing mean and start applying it. So we can say, for example, okay, the observed mean is 9 meters, but the true mean is going to be more like 11. You see, and work to fill in something, and the conditional mean, conditional on being higher than 9 meters, is going to be much higher. So we can work with fat tails, but we just have to be honest and reject all the nonsense of things that do not belong there, not patch up, as many people have patched up. Consequence number 5, I'm reciting consequences the way they're presented in the book. Robust statistics is not robust, and the empirical distribution is not empirical, for the reasons we just saw here, okay, and proved it analytically. That robust statistics only work for tails. Robust statistics being whatever approach non-parametric statistics that really gives you a number that's not going to be shocked by an observation. And here there's an error made in a paper by someone who's a Nobel in economics, where they say historical data suggests that the base rate for a severe single-day stock market crash is relatively low, and how people overestimate it. Effectively, if you read my book, or if you see, my real activities as a trader, and as still is as represented by Universa, that continued with my former colleagues, and where I have a stake. If you see that, you see that we believe that the stock market doesn't, underestimate the tails. The option market underestimated the tail, you see. So we see that analytically, we proved it. No, but here they're doing naive technique, which is basically they take the worst that happened and think that it's not going to be toppled, okay? But if you use extreme value theory and use, proper distribution, you're going to get, what I'm saying, that something may be overpriced, but not based on naive analysis. But this is rampant in economics. Consequence 3, they're not in sequence here. Standard deviations and variance are not usable. Well, why? Well, because for fat tails, mean deviation is a much better method if it exists, and vastly more robust. And I tried to figure out, and this I explained in chapter 3 or in chapter 4 as well. I couldn't understand why people use standard deviation. Standard deviation is a very, very weird operator where you're weighing an observation by itself. So when you have a tail event, okay, you're multiplying it by itself. Rather than mean deviation, you weigh an observation, equally. You weigh all observation equally. So you're weighing it by itself. It turned out that Fisher discovered that it's slightly more efficient for the Gaussian to use standard deviation than mean deviation. More efficient mean, to use the colloquial English, means you need slightly fewer observations to get a good number, all right? But it turned out here, as I show, look, the mean deviation versus standard deviation for a power law that has finite variance. Sorry, let me go back here. Okay, look at the distribution of mean deviation versus that of standard deviation. For the Gaussian, right underneath, slight advantage, but look how the difference is big, which means that standard deviation is going to be much more stochastic and not a good measure, even when it does exist. You see? And here I show what I call the relative efficiency ratio of one versus the other. It's slightly better here, 0.875, one being equal. And then here you go to 8 times better under slightly fatter tail. So basically, variance doesn't mean anything, doesn't represent anything. Under fat tail, I mean, more and more becomes more and more irrelevant. And of course, you have undefined variance or infinite variance. Beta Sharpe ratio and commonly hackneyed financial metrics are uninformative, and that is a very important property. And to give you anyway why the Sharpe ratio, why the variance is uninformative. Another example is, what is the variance of the variance? It's a kurtosis. You see. So kurtosis, if you look at it that way, the variance of the variance, you know that kurtosis pretty much doesn't exist for all of these. And let me give you the first paper really I wrote for International Journal of Forecasting, given that I was never an academic. I just decided to become an academic when I got tired of trading. The first paper, I took this line here, the S&P, 56 years of S&P, and showed that one single day in 56 years represents 79% of the total kurtosis. So it means one observation in 56 years is going to give you 80% of your total, all right? It means that kurtosis number, all right, is not stable, or I mean, to be polite, it's not stable. In fact, it's undefined, doesn't exist. Now, if kurtosis doesn't exist, it tells you the variance is very unstable, is not representative, and that's pretty much what's behind it. So, and then I showed it for all financial instruments, and effectively you have silver, 94% of observation in one day. That was as of 2008. What happens is, as you have more and more tail events, maybe that number will change favorably or unfavorably. In the case of S&P, the largest observation now is maybe only 60% because we had 2 of them. But still, you take the top 3 or 4 observations, they represent, for all of them, close to 99% of kurtosis. Okay, I'm talking about 60 years, 56 years. By now, it's 66 years, all right? That was from 10 years ago. Now, this is going to be sore, okay? Linear least-squares regression doesn't work. When you have, I mean, Amazon, your sales are fat-tailed. I don't know what is thin-tailed in your world. Maybe the height of the members of your team, the weight of the members of your team, their water consumption may be thin-tailed. But believe me, your sales, a lot of these numbers are very fat-tails, or fat-tailed. So when you do linear regression, I don't understand how they do linear regression with fat-tailed, because the very assumption, okay, you require the Gauss-Markov theorem, which requires Gaussianity, okay, or some form of Gaussianity. This is big. Now, I show here, when you regress things that are, like income is very fat-tailed. When you regress income to measures like IQ, because I don't believe in IQ for these reasons, because I saw the paper that said, okay, you're not going to convince me that IQ works because your numbers don't mean anything for me. And let me give you an example here. I constructed an example where I'm regressing a Cauchy, where one variable is Cauchy, I'm regressing it against something else. I know the correlation is 0 by construction, okay? Look at the R square. I know the R square is going to be 0 by construction. Here, most of what you see is 98.5%. So in other words, you have an overestimation of the R square, okay? Aside from the fact that if you violate the Gauss-Markov or find some theorem that allows you to operate this, then I tell you, okay, now show me your numbers, because kurtosis is infinite, okay? And in many of these. So this is another example where you construct something and you see the distribution of R square, all decent, but in fact you know it's 0. Now here, when you go in higher dimension, it's a little sadder, higher dimension, which is why my volume 3 of the technical inserto is focused on higher dimension. The curse of dimensionality, is compounded. So let me give you a little idea here of law of large numbers for PCAs, principal components. I'm sure, practically everybody now does principal components. And this is a one effect. It's not the Wigner effect. It's an effect discovered by Wigner. The Wigner effect is something else. But he looked at random matrices and of course noticed that you have say this is if you generate a random matrix and basically all correlation are 0 in sample, you're going to have higher correlation. This is what you see here. You're going to rank the PCAs. You're going to have a nice PCA ranking that goes down. And as you increase your sample size, because of large numbers, the thing becomes flat. Okay? Now, in this case, I go from n of 30 to n of 1,000. Sorry, n of 30 to n of 1,000. I go for 30 variables from n of 100 to n of 1,000, okay? So here, this is n of 100, n of 1,000. You see, it doesn't take much to show you that there's independence. You see? That is a high-dimensional matrix, so you cannot reduce the dimension, because if correlations are 0, you cannot really reduce the dimensions. So this is the equivalent of law of large numbers, where you don't need much to see the PCA. Okay, and the randomness washes out after a while, because look how quickly the randomness washes out here. At the bottom, you do the same for fat tails. No effect. You will always have a dominant PCA, although we know they're all flat. By construction, they're all flat, and look what you see. And you go from 100 to 1,000, you still see this. You go from 100 to 1,000 to 1,000,000 observation, and you still see this. Okay, and they should be flat. Okay, you need infinity to get flat. So this is, this shows us effectively how we're fooled by randomness by these things. I will not, never miss an opportunity to explain that everything in finance is based academically on portfolio selection, not practically. That requires sigma to the, okay, so it doesn't work, okay? And now there's something they discovered to patch it up about ellipticality, that an elliptically contoured distribution that you can have that if the distribution are elliptical, then maybe even under fat tails these theorems work. Well, I showed that the distributions are not elliptical in finance. And other people have shown that as well. So it's like let not waste time and patch existing methods by let's get deeper. Another way I convey the idea that distribution is not elliptical for someone who doesn't know. You guys know my book sales, so I guess one of the readers of the inserto that's not technical. Okay, now today I'm technical. I'm trying to explain to them why this is nonsense. I would skip all this ellipticality and show this graph. I say everything in finance is based on knowing the joint distribution at infinity. Okay, of all these things. Not only knowing it and with certainty. In other words, that the correlation will not change. It will always be sampling error. This is a correlation of gold to S&P. Look at this. So basically, the only thing that seems to be interesting in this, the only information we get is that the correlation is never above 1 and never below -1. These things are very, very, very unstable. So if correlation is unstable, you cannot work with a correlation matrix. That's sort of like my watered down explanation of the problem. So there are other problems with diversification versus tail hedging. That's technical. There are other problems, but now I'm going to stop. Given that I don't see my audience, I don't know my audience, I've been too technical, less technical, I'm going to summarize. Do I have 2 minutes to summarize, Sam? Okay, so I'm going to summarize in 2 minutes what I said. This is about the statistical consequences of fat tails. I say, now, everybody, you seem to know what fat tails are? Very good, very nice. Now, why on earth are you using standard deviation? Why on earth are you using this? Why on earth are you using PCAs? Why on earth, if you accept that the distribution is not fat-tailed, you cannot patch up the existing methods. So that was sort of like my theme, my main theme. But then within that, we try to look at what we can do, because there are things we can do. The most important thing, the most beautiful thing, I think, is that story about the Dutch people who raise, digs or something. That's we can do, all right? We can definitely figure out where the unseen tail is. We cannot compute it, but we can figure out what it is. Once we figure out something is fat-tailed, we know what action, what policy we should take. We also know how to distinguish between distribution. It's so easy to know if the distribution is fat-tailed. And if it is fat-tailed, it's very, very, very easy to figure out what to do about it. You see? And of course, we love conventional statistical methods. They seem to work in many places, although sometimes not always. But this is the message from here. Stop using bad tools. And if no statistic, you cannot get averages. But there's some techniques we use to get the shadow mean. There are other techniques we use for other things to be able to reject thin-tailedness and then therefore adopt some policies. So there's some ranking of what we call fat-tailedness that we can do. There are a lot of tricks. There are like some details how to compute the Gini coefficient. If you take the Gini coefficient the way they compare it directly from observing the mean, it doesn't work. The way you got to do it is you have a bunch of papers on how to use parametric methods. And it's nice that you can really reject bad science using science. It took me a long time, spend my life working on tricks like that. And even option pricing. People say you can't price option on a fat tail. I say, I've done it all my life. Using an abacus before, using back of the envelope method, and now progressively, more scientifically, using, as we understand the tail. So the story of my life is the story of understanding the tail, and we price options on the fat tails, all right? So there's nothing. It's just that, I don't know, there's something about research that is not very honest, going into areas where people can squeeze a paper because they can publish in Econometrica, and therefore it's fine. And it doesn't work, but you know what? You get a good job, you get publication, good job, you get a good Google Scholar, everybody's happy with that. It doesn't, there's something about this that smells bad. So thank you for listening to me. Thanks, and thanks, Sam.